Welcome back. In this lecture, we will derive a formula for the computations of a Brouwer G-equivariant degree for an isomorphism between the same space. So let me begin with some of notations that we will use later. So let G be a compactly grouped and consider two G orthogonal, let's make sure, two orthogonal G representations V1 and V2. So maybe we should introduce this notation. So for example, we put and we'll write it down L, and this will be G, and this is V1, V2. So this is, by the definition, is the set of all linear operators. So this is V1 to V2, such that A is linear, and B, A is G-equivariant. And this will be just denoted by this. So, once we have this notation, we can also write down if V is exactly equal to V1, which is equal to V2. So this notation will be reduced to this notation. We'll just simply write LGV instead of LGVV for simplicity. And once we have the linear operator, we can also introduce GL of G or GLG of V, which will be the set of all operators belonging to LGV, such that A is invertible. So as I indicated in the beginning, our goal is to derive a formula for the computation of, let me put it clearly, degree, G degree, and I put here A, and here will be BV, where A belongs to the GLG on V, and BV is the unit ball. This is X belonging to V, such that X open unit ball in V. So this is our goal, and we will do it following, let's say, first we need to introduce some additional concepts and say something about the properties of the representations, irreducible representations, and introduce some additional notation. So let's begin with the so-called G-isotypic decomposition. So G-isotypic decomposition of V. So in this case, so again we consider, so if V is an orthogonal but reducible representation, is reducible. Of course, we always assume orthogonal G representation And then of course this means that V is not irreducible so there exists a proper invariant subspace in V. So there exists an invariant subspace V0 subrepresentation. So V0 subrepresentation of V, a proper subrepresentation such that, so we can simply write it down, 0 is different than V0 and V0 is different than V. Then, of course, we have the decomposition, direct sum, the following G invariant direct sum decomposition of V, namely V equals, and here we have V0, and since the representation is orthogonal, then we can take here orthogonal complement, V0 perp, and V0 perp is again a subrepresentation, invariant subspace. So now we can repeat this process. We can just simply ask ourselves, is V0 irreducible? If V0 is not irreducible, we can repeat this decomposition. The same question about V0 perp. So let me write this simply by repeating this decompositions we will eventually obtain a direct sum, decomposition, and we can write it down. This is V, can be written, and I write it down. First component, I put here 1 at the top. Then you have here the second component, 2, plus, and this one will be V. Call this M. So we have a such that each of the subrepresentation Vj is irreducible. So this property that you can always decompose a representation in a direct sum of irreducible representation, it is actually referred as the complete reducibility theorem. So this is, write it down, this is complete reducibility theorem. This is complete reducibility theorem. And of course, once you have such a reducibility, okay, I should also point out, so let's call this one formula star, so to have such a decomposition. So that means simply every representation can be represented as a direct sum of irreducible subrepresentations. It should be pointed out that this decomposition is not unique. That you may have a different subspaces, and you have again a decomposition. So that means it is not a unique way in which the representation V is decomposed. So, however, we will show that it is possible to obtain such a decomposition, which will be called the isotypic decomposition, in which the components will be characterized by the fact that each of the components will only have subrepresentation, irreducible subrepresentations of one specific type. This decomposition will be called the isotypic decomposition. I will explain it in detail in a moment. For a moment, let's indicate another one. I call this one lemma. That's a simple result, lemma, and this is called the Schur lemma. Schur's lemma, and we will just observe this. Actually, you can do it as an observation. Let V1 and V2 be two irreducible G representations and suppose that A just belongs to this is a linear operator, equivariant, G equivariant from V1 to V2. Can we have the following alternative? Can either A is a zero operator or A is an isomorphism. That means simply, in the second case, A belongs to the GL, not GL, okay, just write, maybe we should not write it down. Just isomorphism. That means it's invertible. That means A minus 1 exists. Okay, so proof is very simple. Proof is very simple. So now remember that if, that's a general remark, if A is G equivariant, and it doesn't matter in this case that V1 or V2 is irreducible. If A is invariant from V1 to V2, so this is G equivariant, it means equivariant, then we have kernel of A is a subrepresentation of V1 is a subrepresentation, and also image of A, in this case contained in V2, is also a subrepresentation. Okay, so we have it. This is so if you look at that one, V1 is irreducible. So in such a case, there are only two possibilities. So kernel of A is equal either 0 or V1. And image of A is equal either 0 or V2. And the conclusion follows. And the conclusion follows. So I have it. So now we can put it down and make a conclusion. Let's use this result and let's write down the conclusion. If, and I put it like this, V, and let me point out, in the case of the irreducible representation, I want to use the fancy V. So if V is equal, and put it like this, V naught. V naught is an orthogonal, which is not important, irreducible G representation can, let me write it down, LG on exactly this V naught is a finite dimensional division algebra over the field R. So that's a division algebra. What does it mean, division? That means we have additive structure. That means you can take one operator, add another operator. And you have also multiplication by the real numbers. And in addition, you have operation of multiplication, which is nothing else than decomposition. So with this three operation, the LG becomes an algebra. And this algebra is a division algebra. That means if A is not equal to 0 operator, this will imply that A minus 1 exists. And that's exactly by the Schur lemma. A minus 1 exists. And finite dimensional, yes, this is a vector space, LGV0, clearly is a vector space, SF over R, so this is a vector space. Dimension of this vector space is finite. It's a finite dimension. So now by applying the famous Frobenius theorem, so by Frobenius theorem, we have that necessarily that this LG of this V naught is isomorphic. It is isomorphic in the sense as a real algebra, to either R, C, or the field of the quaternions. So let me write it down. So in such a case, you are getting that LG of this mu 0 is equal, and in this case it will be R or C and or quaternions. So in the first case, if this is true, we will say that this irreducible V0, V naught algebra is of, and we'll call it real type. In the second case, we will say that this is of complex type. And in the last, we will say that is of quaternion type. And now, it's interesting. So basically, look, you can immediately recognize a couple of properties here. So one of the simplest, easy thing to recognize is that, notice that if that this V naught is not of real type, then LG V naught is connected. Sorry. GL V naught is connected. GVL naught is connected. That means all the the group of all equivariant isomorphisms is connected. That's the first one. The second remark is, moreover, if V0 is either of complex or quaternion type, then there exists a complex structure on V0. What does it mean, complex structure? You simply would like to multiply by complex numbers. So that means it becomes, V0 becomes a complex vector space. So in such a case, it is enough to show that there exists, maybe shall I put it like this, there exists an operator I belonging to the GLG V0 such that I square is equal to minus identity. So then if you want to multiply elements, if you want to multiply the elements in V0 by the complex number alpha plus I beta, and I take the vector x belongs to the V0, so I will just simply write this is alpha x plus, and instead of IBX, I will write B, and this is my operator I, which will play the multiplication by complex numbers, X. So that's exactly the multiplication. That means we have a structure, we can define the structure of a complex vector space. And notice that this structure commute, that means this structure is compatible with the group action. So in certain way, this representation is actually a representation which we in the representation called it this is a complex representation. That means this is a representation of the group G by complex linear operators. That means these elements A belonging to the group actions. So let's say like this. This TG that acts from VC to V0 to V0 are the complex linear maps, complex linear operators. They are complex linear operators. You can verify it. Yes. Good. And that means, okay, complex linear operators. Good. And finally, if V0 is of quaternion type, then it is possible we can define, maybe let's say like this, 10, we can define a quaternion structure on V0, namely there exists another operator J belonging to the GLG V0, and this J satisfies the property that J squared is again minus identity, and Ji is equal minus Ij. Yeah. So that will give you the structure quaternion. So in such a case, you know exactly if this is let's say a representation which is not of real type, it has to be as the vector space even dimensional. So let's go. And in such a case, we can also immediately write two very simple conclusions. So write it now as a corollary. And we start with the first approach to the computations of the degree. Namely, we will say like this: if nu0 is an irreducible representation, G representation of G, maybe G representation of real type, so put it like this, a real type, then for every A belonging to GLG E naught, there exists a real number A in R such that A is nothing else than A identity on V. A identity, look here. That's a real number. This is a real number. So what does it mean, real numbers? That basically identity, think about this one, contains R. Just multiplication by identity belongs here. So if this is R, so that means every operator, G-equivariant operator on V0 in this case, is, maybe I write it in red. So put it like this in red. Then we have here R, and here we have A times identity, and then the same, this is this A belonging here, and that means this is contained, so that means actually this is equal, so this must be equal, because what we get. And in such a case, if you would like to compute the, so we have that G degree of this A on this unit ball in the nu naught will be equal. So in the first case, this will be G degree of identity on the BV if A is positive, and in the second case it will be G degree of minus identity B V naught of G if A is negative. If A is negative. And then it's clear that if this is identity, so then we will know, that means simply this is by the normalization property, it is G if A is positive, and still we do not know the degree, but it is something that is minus. We don't let's say this is something which is minus identity on this unit ball in this irreducible representation if A is smaller than 0. How do I get it? Just simply you can connect this A depending on its sign either with 1 or minus 1. And this will give you a homotopy in the GLG. So you have here that the GLG of V naught contains two components, which are exactly the either positive, corresponding to positive, and negative real numbers. So on the other hand, if V naught is not, maybe write it down, is not of real type, then there is nothing to compute, because in this case G-deg of A B on mu naught B will be equal to G. Indeed, Indeed, since GLG V naught is equal either C or H, minus 0 or H minus 0, it's connected, so A can be connected by a path to the identity, and since this path provides us a homotopy, which will be written like that, we have a path, so A, T is the path, so that means simply this is a path. Maybe put it like this, BT. So B is a path from 0, 1 to G, L, G, G naught, and then means this is B of 0, so continuous, and this is equal to A, and B of 1 is identity. Then we are getting here this, but the homotopy property, then you can write it down, degree of B of T on B mu 0 is constant. So that implies that G degree of A on B mu 0 is equal G degree on identity B mu 0, and this